Hello, Earth people. How things are going? My name is Akash, and today I'll talk about how to numerically solve James Cumming model and open quantum system. So that would be in our case, Master's equation in Lindblad form. So before we go into details, let me do some introduction here. So let's talk about qubit, right? So over here, what we are seeing is equation for a two-state of a quantum system, which is shown here, and next to it there is a figure which is known as block sphere, which basically tells us that what in which state our qubit is, with basically a two-state system. So based on vector on this different direction of this block sphere tells us about the different states of the qubit. So only thing that we have to do from the equation is change the theta and phi, and that will give us a vector in another direction, right? So that's our qubit. So there are many different kinds of qubit realizations that has happened over the past few decades. So some of them very successful are superconducting qubit and ion trap qubit. So in my case, I'll talk about one specific type of superconducting qubit, which is transmon qubit. All right, so let's go to the slide and see what that is. So transmon qubit is basically two Josephson junctions which are connected with each other, and there is also a capacitance which is shunting it. So you can see it in our figure B here. So the cross symbol with a box around it, that is our Josephson junction, and it is shunted with capacitance. And if you want to see it in terms of the equation, the Hamiltonian of the transmon qubit, that will be given as 4AC, where n cap here that you are seeing is the charge operator basically tells us that how much charge is there on the Josephson junction island of our Josephson junction, and Ng is basically a noise charge, or we can say a gate charge that is coming because it is connected to other capacitors. And this second term in Ht is Ej cos phi, that is basically the potential due to the Josephson junction here. So next thing that is another Hamiltonian, that is HR, which is the Hamiltonian for the resonator that we are going to couple our transmon with, which is basically a simple harmonic oscillator in our case, right? So another thing that I want to mention here in this slide is the figure C, which is basically two Josephson junctions that what we normally use for the transmon qubit, so that we can vary the flux that is passing through this inner loop of figure C to vary the value of Ej here in transmon qubit, so that we can basically vary the frequency or the level, the difference between ground and energy, ground and excited state, to exactly match with the frequency of the resonator, right? So let me go directly to the next slide and talk about what happens if we connect this resonator and our transmon qubit. So here we have both of the Hamiltonians and the coupling term, which is the last term, h cut g, a dagger sigma minus plus a sigma dagger, and you can see that in the form of a figure. So here in terms of the circuit, over here you are seeing LC circuit here on the left side of the figure. So which is basically the implementation of the simple harmonic oscillator. It doesn't mean that we have directly connected capacitor and an inductor in a lumped way, right? So you can think of it as a 2D microwave resonators, or there are many different, or 3D cavity, and put that as a resonator, right? So if you couple these two together, or let's say what happens if we are not coupling it. So in that case, what you are seeing here in the figure, below figure, is red lines and blue lines. So these red lines and blue lines, so 1 and down arrow and 0 and up arrow, those are degenerate if it is not, if our transmode and resonator is not coupled. But when we couple it, it becomes non-degenerate, and there will be an energy difference of the range of 2G. All right. So that's called Dress states. And what we want to do in our case is to numerically simulate this and try to find the dynamics of this change coming model. So that's what exactly I did. So there are many ways to do it. So one of the ways basically just follow the quantum mechanics of this density matrix. So we'll convert the initial state in terms of a density matrix, and we will evaluate it over the time by solving Schrodinger equation. So, and you will get more details on it on my GitHub. So let me go to the next slide and show you the output of my code. And then what I'll do is I'll compare it with some of the modules which are available online, like Qubit in my case. So there are many other modules available like Qubit to do this implementation. So what you are seeing here in my code is, so initially what we have done is the initial state of our system was in an excited state. So let me just go back to the back one slide. Oh, I can't, I'm sorry guys. So initially it was in excited state, and what's happening is eventually it will come down and becomes 0, that you can see as a orange line in the first part. And so the probability of being in an excited state of a transmon becomes 0, and after some period of time it will become 1. So it is basically oscillating between these two, and that's exactly what we are seeing in both of these implementations. So it has some frequency that is equal to 2G. So that also we can compare here. So both the frequencies in both the implementations are same, and it's giving exactly perfectly same answer for both the implementation, right? So next thing that I wanted to do is to import master's equation, which is like if I connect my transmon to the close to infinite numbers of harmonic oscillators, what will be the evolution of my transmon qubit in that case. So that can be represented as master equation. So over here, these two equations that I have presented here is in the form of Lindbergh, and what I'm gonna do is to implement this and simulate it numerically. So for so that part I haven't yet implemented, and I'm gonna over the period of time using quantum Monte Carlo wave function method. So basically what you are seeing here in the first equation, the first term is the anti-commutator term, which accounts for decay of the excited state, while the second term is a feeding term which accounts for the replenishing of the ground state when the atom makes a quantum jump from the excited state into the ground state. So this division of the relaxation effects into decay and quantum jumps is useful for numerical solutions to the master's equation. One can simulate the trajectory of the atom initially and in the excited state by a deterministic decay and by the non-Hermitian Hamiltonian here, which is followed by the quantum jump. So if we do averaging over many such realizations of this random event, then it will give us the solution. So this method is known as quantum Monte Carlo wave function method. So that's my next goal in this project, to implement it. Till now, please play with what I have for James coming model that you can play around, and see you later. Thanks for listening.